Hi everyone, this is the Unit 2 practice exam. One thing I want to point out on number 1 before we get started. Well, let's just look at all the stuff involved here in this RC circuit. This is an RC. Sure. This is because it has a resistor and a capacitor. We know that the capacitance equals 10.0 microfarads, and the the voltage across the resistor equals 37 volts at time 2 seconds. And the first question wants you to determine the value of the resistance R. The answer is E, 4.3 times 10 to the 5th, or at least in the answer key from the source that I got this question. That is incorrect. The value of the resistance would be this if the voltage across the capacitor was 37 volts after 2 seconds. See, I think they made a mistake right here. And the reason I'm getting to that is the two should be complete opposites of each other. And here's why. If we look at the voltage across the capacitor, well, it should follow the same trend as the charge, right? We remember the equation charge equals Q naught times 1 minus e to the negative t over RC. And because charge equals C times V, then we can say the voltage equals V naught 1 minus e to the negative t over RC. And this voltage is the voltage across the battery, the maximum voltage, 100 volts. Well, that's going to increase with time to approach, V naught, right? When you flip on the switch, the voltage rises really quickly and then approaches that final value of the battery, V naught. That is the voltage across the capacitor, right? Because it makes sense. No current is flowing here, and after infinite time, this voltage here is going to equal the same voltage as the battery, and the voltage on the other side will equal the voltage on the other side of the battery. But the voltage on the resistor is going to do the exact opposite. It's going to start at V naught and approach 0. And the reason that is true is because when you first start out, when you first throw the switch, this side over here will be plus 100 volts, and this side over here will be 0 volts. And then as time goes on, more and more current passes through, builds up charge on this side, all along that side of the resistor. So eventually, when this capacitor is fully charged, there will be no potential difference across the resistor. There will be charge on both sides of the resistor. So that will go to 0. And it will follow the discharging equation like so. Since we didn't really talk about the resistor, I would rather just work this problem as the voltage across the capacitor is 37 volts. All right? So that means we're somewhere right here where up here is 100 volts. And we will use this charging equation. All right. So let's solve this equation for R then. Okay, so we'll bring over V naught, 1 minus e to the negative t over RC. So e to the negative t over RC is equal to 1 minus V over V naught. Now, in order to isolate R, I'm going to have to take the natural log of each side. So negative t over RC is equal to 1, natural log of 1 minus V over V naught. So now I'll just solve for R. R equals negative t over C, natural log of 1 minus V over V naught, which is equal to negative 2 seconds over 10.0 microfarads times natural log of 1 minus 37 volts over 100 volts You throw that into your calculator, you get, I believe it was, let's see, answer choice D, 2.0 times 10 to the negative fifth ohms. Oh, I'm sorry, 10 to the positive fifth ohms. Sorry. Okay? Now, question two asks, how much charge is on the capacitor 2 seconds after the switch is closed? All right. So again, we have to go, since 2 seconds after the switch is closed, V across the capacitor at 2 seconds equals 37 volts. Okay. See, we know that, so then we know what the charge is on the capacitor, because Q equals Q naught times, C times V. That's just our equation for a capacitor. So that's 10.0 microfarads times the voltage, 37 volts. So let's see, that's 37 times 3.7 times 10 to the negative fourth coulombs, which is answer choice C. And this is where I know that they made a mistake here in the question, because if the voltage across the resistor was meant to be 37 volts, then this would not be correct, and this is the correct answer on the answer key. All right, so the next question. An electron is traveling due north. It enters a region that contains a uniform magnetic field that points east. Which direction will the electron be deflected? Well, it's traveling north. So this is velocity, and the magnetic field is due east. Okay, so velocity times magnetic field. The force then is up out of the page. Oh, wait, hold up. Because it's an electron, that means it's going to be the opposite. Jump the gun here. So it's going to be down. Because velocity, magnetic field, force goes up, but it's an electron, so it does the opposite, so it's down. So a particle with that mass and that charge is accelerated from rest through a potential difference of that. The particle then enters a uniform magnetic field. If the particle's velocity is perpendicular to the magnetic field at all times, what is the magnitude of the magnetic force exerted on the particle? Okay. We need to find and the magnitude is QVB sine of theta, or phi, whatever. We know that the velocity is perpendicular to the magnetic field, so theta equals 90 degrees. Sine of theta then is equal to 1. The force equals QVB. We need to find what the velocity is. We have the charge. We have the magnetic field. Yeah, we have the magnetic field. We need to find velocity. Well, we can do an energy thing. So in the beginning to the end, here we have potential energy, electric potential energy, and here we have kinetic energy. So the potential energy, the change in potential energy is equal to the change in kinetic energy. PE initial equals KE final, because the potential energy is converted to kinetic energy. We know the potential energy due to, the electric potential energy is EV, and we can set that equal to 1/2 mv squared. So then V is equal to, let's see, 2 EV. Wait. Okay, this is not an electron. Sorry, you guys. QV. I don't know why I thought it was an electron. So 2QV over M and the square root of all of that. So I'll put that over here. Force equals Q times the square root of 2QV over M, where V now is the potential difference. I should probably put the delta in there to remind us, times B. All right, so now it's just plugging all this stuff into the calculator. Squared, so this, actually, do it like this, Q to the 3/2, because that's the same as Q times Q to the 1/2, so Q to the 3/2, 2 delta V over M B. Q now is plus 3.20 times 10 to the negative 19th coulombs, and that's raised to the 3/2. You don't have to do the 3/2 thing if you don't want to. 2 times the potential difference of 2.45 times 10 to the 6th volts over the mass, and the negative 27th kilograms, and the magnetic field of 1.60 Tesla. All right, let me put all this stuff in. And that's raised to the 3 divided by 2 times, let's see, second square root, 2 times 2.45. So the force then is 7.87 times 10 to the negative 12 newtons. And thank goodness that's one of our answer choices. Okay. Two particles move through a uniform magnetic field that's directed out of the plane of the page. The figure shows the path taken by the two particles as they move through the field. The particles are not subject to any other forces or field. Which one of the following statements concerning these particles is true? Well, the statements are regarding the charge. So let's see. If the velocity of particle 1 is in this direction and the magnetic field is in that direction, so the magnetic field, or I'm sorry, the magnetic force should point outward, but it doesn't. We know that the magnetic force points inward. How do we know that? Because it's moving in a circle. So something must be providing the centripetal force, and we know there are no other forces but magnetic force. So the centripetal force must equal the magnetic force, and the only way for that to be true is if this were a negatively charged particle. Because velocity, field, the force on a positive charged particle would go outward, but a negative particle would go inward, so one must be negative. Let's think about this one. We know this one must have a centripetal force that equals the magnetic force. So velocity, field, okay, the force should point outward if it were positive, but it's pointing inward, so that must be negative too. So particle 1 is negative, particle 2 is negative. The figure shows two concentric metal loops, each carrying a current. The larger loop carries a current of 8 amps and has that radius. The smaller loop has different radius. What is the value of the current in the small loop that will result in 0 total magnetic field at the center of the system? Well, let's think about this. At the center, we have, if we use the second right-hand rule, so the current going around the outer loop is going to end up with a magnetic field we'll say BL for B larger, that will be out of the page, and the current from the inner loop would go clockwise, so it would be smaller. That will create a field that's into the page. So then BL plus BS must equal 0. That's the constraint. 0 total magnetic field. And we know that the smaller one is going to be in the opposite direction, so we could put a negative sign in there. We could just say the magnitude of BL equals the magnitude of BS. And we also further know that the magnetic field due to a loop is equal to mu naught I over 2R. So I'll just put all this information in. Mu naught IL over 2RL equals mu naught I small over 2R small. So mu naught cancels, and let's just solve for IS. Oh, 2's cancel as well. So IS equals RS over RL times IL. RS is 0.040 meters over RL, which is 0.060 meters, times the current in the larger ring, which is 8.0 amps. .33 amps. A. So a magnetic field is directed perpendicular to the plane of a rectangular coil to induce an average EMF of negative 2.5 volts in the coil. The magnetic field is increased during some time interval. Determine the time interval. Okay, so let's just write down all the stuff that we have. We have area equals length times width, which equals 0.15 meters times 0.30 meters. The number of loops equals 240. The average induced EMF is negative 2.5 volts. And the change in the magnetic field equals final minus initial. Well, I'll say B final minus B initial, which is 1.8 Tesla minus 0.1 Tesla. And we don't know what the time interval is. Well, if you remember Faraday's law of induction, EMF equals negative N delta phi over delta T, which equals negative N delta B A cosine phi over delta T. And we have no one talks about the orientation changing. We know the area is not changing, so it's just the magnetic field that is changing. So negative N B cosine phi is it's perpendicular. Yeah, it's perpendicular. So cosine of the loop is perpendicular to the magnetic field. So that means it's parallel to the area vector. So cosine phi is 1, phi is 0. So negative NB, pull the area out because that's not changing. So that's delta B over delta T. So I'll solve for delta T. And now it's just a matter of plugging in numbers. Negative 240 loops times the area, which is 0.15 meters, times 0.30 meters, times the change in B, which is 1.8 Tesla minus 0.1 Tesla, over the induced EMF, which is negative 2.5 volts. Just plugging it into the calculator. .344. 7.34 we'll call it. Which is answer choice E. For the next question, we're going to use this loop. 3 Tesla magnetic field is normal to the plane of the conducting loop, so we know phi is going to equal 0. And resistance equals 1.5 ohms, and the radius equals 0.024 meters. Magnetic field is directed out of the paper. Okay, so let's see. What is the magnitude of the average induced EMF in the loop if the magnitude of the magnetic field is doubled in 0.4 seconds? Okay, so let me just copy down B equals 3.0 Tesla, phi equals 0, R equals 1.5 ohms, and the radius equals 0.024 meters. So the average induced EMF we know is just negative N. We also know N equals 1 because it's just one loop of wire. Change in phi over change in phi and over change in t is negative N. Change in B, A cosine phi over delta t. Cosine phi is 1. In this case, we know the magnetic field is changing, so negative N A delta B over delta t. And we know B final equals 2B initial, delta t time equals 0.4 seconds. Okay. Area is negative N pi r squared, delta B over delta t, N pi r squared times B final minus B initial. So then, that's going to equal negative N pi r squared 2B naught minus B naught over delta t. So just plug that in. So the EMF is equal to negative N pi r squared B naught over delta t. Negative 1 times pi times r, little r, the radius, squared, times the original magnetic field. Oops, not pi, it's Tesla. Or the change of time, 0.4 seconds. So negative pi times 0.024 squared times 3 divided by 0.4. So the induced EMF is negative 1.36 times 10 to the negative second volts. Or which would be option C up here. Okay, so what is the average current around the loop if the magnitude of the magnetic field is doubled in 0.4 seconds? So same situation as above, but now we have the induced EMF, so we know EMF equals IR equals EMF over R, so that equals 0.014 volts over the radius 1.5 ohms. Equals 9.33 milliamps. Okay, so we have two options here, clockwise and counterclockwise. So now we're going to have to figure out which one it is. Okay. So then, the magnetic field is coming up out of the page, and it's increasing. So the current has to resist that. So that means the induced field is going to be downward towards the page, which would mean the current would have to be clockwise. So that is option D. Okay, next problem. We have a long straight wire. It's just in the same plane as a rectangular conducting loop. The wire carries a constant I shown in the figure. Which of the following statements is true if the wire is suddenly moved toward the loop? It's regarding the EMF. There is going to be an induced EMF and an induced current. As it's moving down, the magnetic field is getting stronger. B increases as you get closer to the loop. So that means the magnetic field is getting stronger. Magnetic field, according to right-hand rule, must be into the page. So that means a current must be induced in here that creates a magnetic field out of the page to combat that. So that means if the field is out of the page, the current must move to the right. An induced current that is counterclockwise around the loop. That's D. Is that the last one? Oh, last problem. A metal ring is dropped from rest below a bar magnet that is fixed in position as suggested in the figure. An observer views the ring below. Which one of the following statements concerning this situation is true? Okay, so we're going to see if there's a current induced. The magnetic field from the North Pole flows outward. So as the ring gets farther away from the magnet, the field flowing through the ring gets weaker and weaker. So the flux gets lower and lower. So that means a current must be induced in this ring to combat that change, or in other words, increase the flux to get it back to where it was before it started falling, right? So that means that if we want a magnetic field going upward, that means there must be a current flowing around this way, counterclockwise. Wait, hold up. No, take that back. It will flow counterclockwise as observed from above, because we're kind of looking at it from above. From the viewer down below, it's going to flow, it's going to be clockwise, look, because this guy's looking at it from below, so that direction is clockwise. So there is an induced current, and it's flowing clockwise. All right, that is the practice exam. It should be very similar to the test. I think if you can do this practice exam well, you can do the test well, so good luck.